What we want to be able to do is not only graph inverse functions, but evaluate them and apply our knowledge of calculus to these things. And but we'll start with the, or at least continue with the pre-calc applications. And well, applications is a strong word, but applying our knowledge of the graphs of inverse functions. So when it comes to something like numbers, what? I don't have numbers for them. The two examples that you see here, something to keep in mind, the unit circle is still a thing. Right? If you know your unit circle relationships, then things get to be a lot easier. I do want to kind of call back to something I mentioned in the previous video, previous page, is that when you have something in the form of y equals sine, for example, of x, the x is your angle, the y is the ratio. All right? That looks pretty hideous. All right, so ratio and the angle. So the roles reverse when you find the inverse. And that would be, and we could just do the quick switcherooski on the x and y, but we could also actually solve for the y. So, but I'll just kind of cut to the chase here because we explored it enough on the previous page. If I say y is equal to the inverse sine of x, the x is now a ratio and the y is an angle. So when you're solving for a value in an inverse function, you're actually solving by substituting in a ratio and getting an output that is the angle. All right. So this actually gets, I don't know, translated or interpreted as a question of what angle in the unit circle has a sine ratio of -1/2. So if you know your unit circle, then you're going to be in pretty good shape. All right. So what I'll do is I'll actually just put in a unit circle here and we'll take a look at it real quick. Just kind of pop it right there. That's good enough. And so as we look at the unit circle, you see again we're looking for a sine ratio of -1/2. The sine ratio is really just a y value. All right, because remember every coordinate on the unit circle is x comma y. All right. Well, that's the most obvious thing ever. So x comma y gives us cosine comma sine. All right. So I'm looking, when I'm looking for the sine ratio, I'm looking for the y value. So a y value that is -1/2. So I just kind of hunt around. I got a -1/2 here, and I got one right here. All right. So my arc sine function, I could say, just by looking at the unit circle, would be, I'll write it again, arc sine 7 pi over 6 and 11 pi over 6. The problem is we have to be mindful of the domain. All right. So just kind of going back here, just looking at the sine ratio, the domain here has to exist between -pi/2 and pi/2. So I'd be like, well, does this one exist between -pi/2 and pi/2? So no. Does this one? The number itself, no. The location, yes. All right. So what I would do is I would translate that to be a -pi/6. That's equivalent. The coterminal angle, same location in the unit circle, so it gets the job done, but we would not want the 11 pi over 6. All right, we'd have to replace it in order for it to be part of the domain. All right. Same idea for the inverse cosine. Oh, I wanted to copy paste. No? Okay. I'll just refer to it. So what angle in a unit circle has a cosine ratio of negative radical 2 over 2? All right, that's really what it's asking. I can actually, now that I think about it, I can just pop it in again. So negative radical 2 over 2 for x. So just kind of hunting around. And there we go. All right, so I'm looking for the one that's also going to be in the correct domain. All right, the cosine ratio only exists, and I'll write them both down, but it only exists in the 0 to pi domain. All right, so there's no way we're going to get the 5 pi over 4 in that domain even by finding coterminal angles, so we dismiss that one. So the only relevant one would be the 3 pi over 4. All right, so we could also put it in the calculator. Radian answers, they always come up a little funky in the calculator, but there's a way around that. So I get this decimal here. There's two ways to handle it. One way would be to say, well, you got to figure it's a multiple of pi. So what you can do is divide out pi, see what the decimal is, convert it to fraction form if you don't recognize it, it's 3/4, and then slap the pi back on. The other way to do it, which is a way I don't particularly care for, because I find that students forget to fix their calculator afterwards. You put your calculator in degree mode, do the work, but then you got to make sure you put your calculator back in radian mode when you're done. Otherwise, yeah, you'll get that question right, but then you'll get every question after that wrong, right? So you get 135 degrees, which you would then convert over into radians, all right? So there's pros and cons either way. Or you can go to Desmos. So inverse cosine function, inverse cosine negative the square root of 2 over 2 gives you that funky decimal, and then you go from there. All right. Again, assuming that it's some multiple of pi. So divide this number by pi. You get the 0.75, or at least Desmos trying to tell you 0.75. It's working with approximate value, so it's a little iffy, but 0.75, 3/4, 3/4 pi, 3 pi over 4. All right. Now these other ones are just flat out telling you to do it in the calculator, so they're calling for decimal answers. Arctan of negative 0.3, so about negative 0.291. Arc cosecant, arc cotangent. You're like, oh no, there's no arc cosecant, arc cotangent. There is on Desmos. All right, so now you're sold. If you weren't before, you are now. So arc cosecant of negative 2.4. You got about negative 0.430. I mean, it's really negative, negative 0.429775. But when you go to round the 9, that forces the 2 up to a 3, so that's something. All right, so you could do that. That would work the same way for the cotangent. There is a workaround that allows you to do it on the TI. Let me just show you real quickly. So if I know that y is going to be equal to the inverse cosecant of negative 2.4, one thing I could do is take the cosecant of both sides, write this as 1 over the sine, take the reciprocal, and then find the inverse of both sides. So what I'm essentially getting at here is that I could find the inverse cosecant of negative 2.4 by taking the reciprocal of the function and the reciprocal of the ratio. All right, so let's verify that very quickly. And there we go. So we got negative 0.43-ish before, we got negative 0.43-ish now. Then for the inverse cotangent of 3, all I would have to do is find the inverse tangent of 1/3. Which is about 0.322. And if we crank that into Desmos, we could again do that with a built-in function, inverse cotangent of 3. You see that it ends up being the same thing. To evaluate trig functions of inverse trig functions, this is leading up to what we're going to do in terms of derivatives and antiderivatives. So yeah, we could pop this into a calculator, but that's not going to help us with the variable components. Right, so what I'm going to do is show you a triangular approach. Right, like I said before, the value or values that are contained within an inverse trig function is a ratio. The result of an inverse trig function is an angle. Alright, so this angle we can call theta. So in effect, this is giving us really the sine of theta, where theta is equal to the arc cosine of 4/5. Alright, so the best way to tackle this, it actually it reminds me of what, early in my teaching career, I was teaching an Algebra 2 class, and there were these problems where it said if the cosine of theta is 4/5, just stealing this value here, what is the sine of theta? And it's like, what on earth could this possibly be useful for? And so here we are. All right, so that's really essentially what it's asking. All right, so what I'm going to do is draw a triangle. I'm going to draw it in the first quadrant because we're looking at an angle in which sine and, well, I was going to say sine and cosine are positive, but we don't really know that for sure. We know that the cosine ratio is positive. All right, and so that could put it in the first quadrant or the fourth quadrant. All right, so we can draw a first quadrant triangle and see how it goes, and if there's any reason to think that the fourth quadrant triangle would be any different, then we'll make an adjustment. All right, so I'll draw the axes also, because it's always a good idea to keep that in mind when you're tackling these kind of problems, that it is still a coordinate, XY coordinate axis situation. All right, and this is the reference angle, unknown reference angle. Now that arc cosine of 4/5 equal to theta, well, I could take the cosine of both sides and get cosine of theta is equal to 4/5. It makes it a little bit more obvious that the 4 is the adjacent side and the 5 is the hypotenuse. All right, so adjacent, hypotenuse. Opposite side would have to be 3 because it's a 3, 4, 5 right triangle. All right, so now if I want the sine of theta from this triangle, sine of theta would be opposite over hypotenuse, 3/5. If theta is arc cosine of 4/5, I'm really, just by finding sine of theta, I'm really finding sine of the arc cosine of 4/5, which is 3/5. All right. Now, if it is a fourth quadrant situation, then we could end up with a negative value. All right. So let's just kind of pull that off for a second here, because our cosine is a negative or a positive ratio. ASTC tells us that it could be in the fourth quadrant as well. If I can get this to look kind of straight. All right, adjacent over hypotenuse, 4/5. That would make this a -3. All right, so if it's this triangle, all right, so it's an either or situation, so it could be an or. Sine of theta would be -3/5, in which case the sine of the arc cosine of 4/5 could be -3/5. All right. Now, just kind of thinking back here, though, we have to make sure that we're mindful of the domain. All right. Domain, range. So the arc cosine function only exists it wouldn't be a theta, or cosine of x is only going to exist between 0 and pi. All right. So when I go to make my triangle here, here's 0, here's pi, anything in the bottom half is going to be eliminated, so none of this would hold up, and so the only one that would actually work would be the 3/5. All right, so under ordinary circumstances, we could say it's two possible solutions, but because of the restrictions imposed based off of the fact that it's our cosine function, we limit ourselves to the one solution. All right, so that's that. Now, and that's strictly numerical, because when you get into the variable stuff, things get a little kookier. But when it's numerical, you could put this in a calculator and call it a day. I mean, I just say, well, would I have to do any of that? I would just type in sine of the inverse cosine of 4/5, and you're like 0.6, 3/5 done. It's like, why would I have to do any of this other stuff? Well, for this kind of problem, you wouldn't, but we need to learn how to do it for the cases where it's really not this kind of problem. All right, so that's where we're at. So let's take a look at the next one. Sine of the arc cosine of x, just the plain old x. How difficult could that be? Well, let's take a look. All right, so we'll start off with the same kind of deal. We're looking for the sine of theta, where theta is equal to the arc cosine of x. And if I take the cosine of both sides, I get cosine of theta is equal to x, but that x could be thought of as x over 1. Again, adjacent hypotenuse. So I'll draw the diagram. I'm going to kind of steal my work here a little bit, or at least as much as I can. Alright, so I lost a piece of it, but that's alright. All right. So in terms of the ratio, well, that x could be, it could be positive, it could be negative. We got a lot of stuff going on here. Now the hypotenuse we know is going to be equal to a 1, so that's something that we can run with. All right. Now if that adjacent side is x and we assume that x is positive, then the missing side here, based off of the Pythagorean theorem, you know, a squared plus b squared equals c squared, would be looking at x squared plus some unknown, I'll call it b squared, is equal to 1 squared. B squared is 1 minus x squared, which makes b equal to the square root of 1 minus x squared. All right, so that's my missing side. Now if I want the sine of theta, opposite over hypotenuse, I'm going to get the square root of 1 minus x squared over a 1. Now you just kind of play it out. Well, where else could I have put the cosine function, or I'm sorry, the triangle? I could have put it in the second quadrant. Because we could make the assumption that x is negative. I wouldn't put negative x. If I can make this look nice, I'd really appreciate it. I wouldn't make it a negative x. I would just put an x here with the assumption that x could be a possibly a negative value. All right. But every other ingredient's going to boil down the same way. I'd get the square root of 1 minus x squared here. I'd get a 1 here. And when I go for the opposite over hypotenuse, I would get the same ratio. All right, so there would be no change. So the moral of the story here is just leave it in the first quadrant. All right, it's more often than not, it's not going to matter. When it does matter, it'll be pretty painfully obvious that it does matter and why it matters. All right, so you got that. Now I'm looking for the sine of the arc cosine. Well, that whole triangle came from the arc cosine ratio. So, and since theta is defined as arc cosine of x, I can now make the substitution: sine of the arc cosine of x is equal to the square root of 1 minus x squared. All right. So now it's kind of getting to the point where we would start thinking about, well, why? Why would we do any of this? Well, we know how to take the derivative if you have a radical function. We know how to take the antiderivative with u substitution to some extent. All right? But so far, we don't know how to take the derivative or antiderivative if there's an inverse function. But what we just learned is, well, if I have an inverse function, maybe I can convert it over into a radical function and use that instead. All right, so that's kind of what we're getting towards. All right, so part C, same idea. We're going to draw a picture. We'll just draw it from scratch here. All right, as we know, we're dealing with a ratio, or we should know now. So this whole thing, again, is theta. All right, theta is equal to the arctangent of x. All right, so if that's the case, then tangent of theta is equal to 3x. And ultimately, we're looking for secant of theta. All right, so tangent is opposite over adjacent. Opposite side 3x, adjacent side a 1. Using the Pythagorean theorem, square each leg, slap a radical over the whole thing, and you have your hypotenuse. All right, so that's my theta, or at least the triangle that emerges from the knowledge of the inverse trig function, which is defined as theta. It's a mouthful. So I need secant. Secant is hypotenuse over adjacent. So secant of theta is the square root of 1 plus 9x squared over a 1. And since theta is the arctangent of 3x, we would say secant of arctan of 3x is equal to that radical, the square root of 1 plus 9x squared. So again, I kind of pose the question, which would you rather take the derivative or antiderivative of? Secant of arctan of 3x or the square root of 1 plus 9x squared? At first glance, it might seem like the way to go would be the square root of 1 plus 9x squared. All right, and we'll learn more down the line, and it'll help you really make an informed decision, but it certainly looks a lot nicer.